Perfect. Thank you so much, Advantage, for the opportunity to present on data science projects for oil and gas. And I understand it's early in the morning in the United States. It's at 7 a.m. Central Standard Time. And I know it's 5:30 p.m. in India Standard Time. I'm curious to know if you can type in the chat what time it is in your part of the world. Feel free to do that. And then I'll go ahead and start sharing my screen.
Ma'am, you are the host right now, okay?
Yes, I'll
On
share my.
Yeah, thank you, thank you.
Perfect. I'm going to put this in presentation mode. All right, everyone. So today, going to talk about data science projects in the oil and gas industry. And I'm particularly going to talk, and I can't see anyone right now, so feel free to chime in if you have any questions or type in the chat if you have any questions. And chances are I'll probably save questions until the very end because there's quite a bit of material to go over with for this presentation. Let me try this. Okay. As an outline of the presentation, I'll talk about the objectives of the webinar, significance of data science in oil and gas, what exactly is data science, real-world project examples, best practices and pitfalls, and tools, platforms, and career pathways. So the objectives of this webinar, there's quite a few. I want to demystify data science for energy professionals by explaining key concepts, tools, and workflows, real-world use cases, value creation, so show how data science is important, introduce practical tools, demonstrate project workflows, discuss common pitfalls, explore how to be ethical in deploying data science projects, how to convince non-technical stakeholders, provide career and upskilling pathways, and then so what are some career pathways you can have with an oil and gas career with having data science in your toolbox? And then, of course, I hope this sparks some creativity or inspiration in you to have your own data science initiative in oil and gas. So there's quite a few objectives that I'd like to accomplish in this webinar. I really hope that you guys have a ton of ideas when discussing data science in your workflows in your daily oil and gas jobs. I'm assuming everybody has an oil and gas background, or for those that don't have an oil and gas background, you have some interest in oil and gas in having some data science fluency or data science application into oil and gas. So now I'm going to talk about the significance of data science in oil and gas. Like, why in the world are we talking about data science in oil and gas? It increases operational efficiency, it enables predictive maintenance, and accelerates reservoir characterization, among other things. So it optimizes drilling parameters and well placement using predictive models, reduces downtime through real-time monitoring and anomaly detection, improves asset utilization and crew scheduling with data-driven logistics, enables predictive maintenance, uses sensor data to forecast equipment failures before they occur, minimizes unplanned shutdowns, and extends asset life. And then for accelerating reservoir characterization, clustering and regression, sweet spots and bases, and dynamic modeling with surrogate models. So there's quite a bit of significance in oil and gas, and there's quite a bit of application to oil and gas with data science. Improves production forecasting, supports ESG and sustainability goals, and unlocks value from legacy data. So for improving production forecasting, you can build time series models to predict flow rates, pressure, and decline curves. Scenario planning for lift optimization and field development. And then surface and subsurface data for holistic forecasting. So like if you have constraints in your facilities, how does that affect your decline curve? So supports ESG and sustainability goals. You can track emissions, water usage, and energy consumption, automates ESG reporting and stakeholder discussions using natural language processing, and identifies opportunity for carbon reduction and CCUS optimization. And then for unlocking value for legacy data, digitizes and mines historical reports, logs, and spreadsheets, uses natural language processing to extract insights from unstructured documents, and enables AI-powered search and summarization for technical reviews. So let's see. And then you have informed strategic decision making, democratizes technical insight, and drives innovation with competitive advantage. For strategic decision making, dashboards and visualizations, investment planning, risk assessment, portfolio optimization, transparency and trust across internal and external stakeholders. So then you have technical insight. You make complex data accessible to non-specialists and no-code tools, empowers field engineers, educators, and civic leaders to engage with data, bridges domain expertise with data fluency across teams, and then drives innovation and competitive advantage. Rapid prototyping of AI solution for field challenges, supports digital twin development and autonomous operations, and positions companies as leaders in digital transformation and energy transition. There's quite a bit as far as significance in oil and gas. But at this point, I'm probably beating a dead horse. So now let's talk about the evolution of data science throughout oil and gas. This is not a holistic history of the evolution of data science in oil and gas, but it's close enough. So let's talk about manual and rule-based analysis. There's a reliance on spreadsheets, deterministic models, and expert judgment. And truth is, like, there's still some of this even today. Data is stored in siloed system with limited interpretability or interoperability, reservoir modeling, production forecasting done using physics-based simulators, which nothing is wrong with that. It just takes a long time to develop a model and then simulate it. And then decision making was slow, localized, and often reactive. So this is before you implement data science, or this is like data science in its infancy. So now you have digitalization and SCADA integration. You have widespread adoption of SCADA systems and digital sensors, real-time data collection from wells, pipelines, and facilities, emergence of centralized data historians, basic analytics and visualization tools for operational insights. Then you have big data and advanced analytics. You have explosion of data volume from seismic drilling and production operations, introduction to Hadoop, Spark, and cloud platforms, use of machine learning for predictive maintenance, well performance modeling and anomaly detection. Data science teams form within E&P companies to support decision making, and a growing interest in integrating structured and unstructured data. So that's like logs and reports. So that's like big. So that's when you start hearing about big data and advanced analytics in the 2010s. And then you start looking at SCADA back in the 2000s. So now let's talk about AI and deep learning adoption. So again, AI has been there since for quite some time, really. It's now that people are starting to talk a lot about AI or generative AI. And people are starting to have this doubt of artificial intelligence, where I don't think there should be. So there's a deployment of neural networks for seismic interpretation, image analysis, and natural language processing. Surrogate modeling used to accelerate reservoir simulation and CO2 plume prediction. Natural language processing models applies to ESG reporting, permit analysis, and legacy document summarization. There's a rise of auto ML platforms and no-code tools for democratizing access to modeling. And then data science began influencing to strategic planning, not just operations. So now we have the AI-driven transformation ESG integration. AI is embedded in field operations, emissions tracking, and CCUS workflows. Data science is used to optimize carbon intensity, water usage, and energy efficiency. You have the integration of geospatial, satellite, and Internet of Things data for environmental monitoring. You have AI-powered search and summarization tools transforming technical archives. And then you have a growing emphasis on explainability, ethics, and governance in each model deployment. Now we'll talk about the future trajectory, where you have real digital twins for entire fields and facilities, autonomous drilling and production optimization using reinforcement learning. Then you have AI agents collaborating with engineers for scenario planning and risk mitigation, expansion of data science into community engagement, education, and policy modeling, and then standardizations through platforms like OSDU to enable cross-operator collaboration. So I know I should have started the presentation by defining what data science is, but I wanted to just talk about the evolution of data science first and then what we were going to capture from this presentation. So what exactly is data science? It's an interdisciplinary field extracting insights and knowledge from structured and unstructured data, combined stats, computer science, domain expertise, and machine learning to solve complex problems, enables data-driven decision making across industries, from oil and gas to healthcare and education. So now there are core components, and we're going to go through each one of them in data science. Data collection, data cleaning, exploratory data analysis, feature engineering, modeling, evaluation, visualization, and deployment. So for data collection, you have gathering raw data from sensors, databases, APIs. That in itself is a lot of work. Data cleaning is where you spend the most amount of time, where you remove errors, handling missing values, and standardizing formats. And then you get to the fun stuff where you do exploratory data analysis, which is identifying patterns, trends, and anomalies using statistical methods. Then you have feature engineering, where you're creating meaningful variables from raw data to improve model performance. Then you have modeling, which is applying algorithms such as regression, classification, and clustering to make predictions or segment data. Then you have evaluation, measuring model accuracy, precision, recall, and robustness. Then you have visualization, which is presenting insights through dashboards, charts, and interactive tools. And finally, you have deployment, which is integrating models into real-world systems for continuous use and feedback. So we're going to go through all of this in terms of data science in oil and gas. So the tools and technologies used in data science. Mostly it's Python. There are some people that use R, and there's definitely a lot of people that use SQL. I haven't heard too many people using Julia. But as far as libraries go, a lot of people use Pandas, scikit-learn, TensorFlow, PyTorch, and Matplotlib for plotting. Platforms, Jupyter Notebooks, Azure ML, Google Colab, Power BI. And then the techniques used is machine learning, deep learning, natural language processing, time series analysis, and geospatial modeling. Now, the applications in oil and gas, you can do predictive maintenance, production forecasting, reservoir characterization, CO2 injection, natural language processing for technical reports, and then field crew optimization. For predictive maintenance, you're forecasting equipment failure using sensor data. For production forecasting, you're modeling well performance over time. Reservoir characterization, you're clustering subsurface data to identify phases and zones. CO2 injection optimization, you're using surrogate modeling for plume migration and sweep efficiency. Then for technical reports, you're summarizing legacy documents and ESG disclosures. And then for field crew optimization, you're routing and scheduling using geospatial and operational data. And then for strategic impact, you're improving efficiency, enhancing decision making, driving innovation, and supporting sustainability and democratizing insight. So you're automating analysis that reduces manual effort. You're providing evidence-based insights for operations and strategy. You're enabling new products, services, and workflows. You can track emissions, optimize energy use, and informs ESG strategies. And then you're making complex data accessible to non-technical stakeholders. I think that should be the main objective as to why you're thinking about data science in oil and gas, not just learning about it and upskilling yourself, but making sure you're breaking down something so complex and something so messy to something that's pretty simple. For those of you that are not on mute, can you mute yourself? So now let's go into data cleaning. It's the process of detecting, correcting, removing errors and inconsistencies in data sets to improve quality and usability. You ensure that data is accurate, complete, consistent, and properly formatted before analysis and modeling. It's often considered as the most time-consuming step in data science. It can take up to 50% of a project's effort. So here are the core tasks in data cleaning that you may be thinking about. This is the non-sexy part of data science. This is the handling missing values, removing duplicates, standardizing formats, correcting errors, filtering noise, validating data types, and resolving inconsistencies. For handling missing values, there's imputation, deletion, or flagging incomplete records. Removing duplicates is identifying and merging redundant entries. Standardizing formats, you're aligning units, date formats, and naming conventions. You're fixing typos, mislabels, and out of range values. You're removing irrelevant or low quality data points. Then you're ensuring fields match expected formats like numerical or categorical. And you're harmonizing data across sources or systems. So the application of data cleaning in oil and gas is plentiful. You have well log harmonization, ESG and emissions reporting, and production and SCADA data. For well log and harmonization, you're cleaning and aligning logs from different vendors, vintages, or formats. You're standardizing curve names, units, and depth intervals for modeling. And then you're preparing data for facies classification or reservoir simulation. For ESG and emissions reporting, you're validating methane, CO2, and water usage data across assets. You remove inconsistency in reporting formats and units. You ensure compliance-ready datasets for stakeholder disclosures. For production and SCADA data, you clean time series data from sensor and control systems. You handle gaps, spikes, calibration errors, and flow rates or pressures. And then you enable reliable forecasting and anomaly detection. And then you got CO2 injection and CCUS monitoring, legacy document digitization, and then field crew logistics optimization. Align injection logs, seismic data, and plume tracking methods, remove noise, and harmonize special temporal formats. Prepare data sets for surrogate modeling and sweep efficiency analysis. For legacy document digitization, using AI to clean OCR text from scanned reports and logs. Resolve formatting issues, misreads, and metadata gaps. Enable natural language processing based summarization and search across archives. Then you have field crew and logistics optimization. You clean crew dispatch records, job logs, and location data. You standardize skill tags, job codes, and timestamps. And then you improve routing algorithms and workforce planning. So best practices for data cleaning in oil and gas: use domain-specific rules, automate repetitive tasks with AI agents or ETL pipelines, document cleaning steps for reproducibility and auditability, collaborate with SMEs to validate corrections and assumptions, and then integrate with data governance frameworks like PPDM or OSDU. So now we're getting to the fun part, exploratory data analysis. So this is the initial phase of data analysis where analysts explore data sets to uncover patterns, spot anomalies, test assumptions, and generate hypotheses. It involves visualization, statistical summaries, data profiling to understand the structure and quality of the data. EDA is non-model driven. It's about insight, not prediction. So usually people do a bunch of EDA and they stop and they don't necessarily develop a model because a lot of it is just trying to develop insight from data. So core techniques: descriptive statistics, data profiling, visualization tools, correlation analysis, dimensionality reduction, or time series exploration. So descriptive statistics is like using mean, median, mode, standard deviation, and skewness. Data profiling is missing values, duplicates, outliers, data types. So just figuring what those are. You go through EDA and data cleaning. You can go back and forth on that too. You have visualization tools like histograms, box plots, scatter plots, heat maps, pair plots. You do correlation analysis, like identifying relationships between variables, dimensionality reduction, and time series exploration. So trend, seasonality, and lag analysis for production or sensor data. For dimensionality reduction, you may hold a principal component analysis, so that's for a lot of columns in the data. So applications of EDA in oil and gas is well log interpretation and drilling performance analysis, among many others. So explore gamma ray, resistivity, porosity, and density logs. Detect anomalies or missing zones before modeling. Identify facies, clusters, or reservoir boundaries visually. Then you have drilling performance analysis. You analyze rate of penetration, torque, weight on bit, spot inefficiencies or hazardous conditions in drilling operations, and compare performance across rigs, formations, or crews. And then you do production data exploration, ESG emissions profiling, and CO2 injection and CCUS modeling. Visualize flow rates, pressure, and temperature over time, detect production decline and sudden drops, correlate subsurface and surface variables for optimization. And then we've already talked about ESG and emissions profiling, and then CO2 and CCUS monitoring. You're visualizing injection rates, pressure buildup or sweep efficiency, and then you're detecting anomalies in storage, integrity, or leakage risk. Then legacy data harmonization, profile historical data sets for inconsistencies and gaps. You can align formats, units, and naming conventions, and then prepare data for natural language process-based summarization on AI search tools. Best practices for EDA in oil and gas. Use domain knowledge to interpret patterns meaningfully. You want to automate profiling for large data sets using Python or Spotfire. You want to document insights and assumptions for downstream modeling. You want to collaborate with SMEs to validate findings and refine hypotheses. And you want to visualize before modeling. Exploratory data analysis often reveals what models miss. Now we're going to talk about feature engineering. So it's the process of creating, selecting, transforming, or extracting variables from raw data to improve the performance of machine learning models. It bridges the domain knowledge with statistical and computational techniques to make data more informative and model ready. It's often considered the most critical step in building effective predictive models. Core techniques: transformation, encoding, aggregation, interaction features, temporal features, domain-specific extraction, and dimensionality reduction. So core techniques for transformation: log scaling, normalization, and standardization for numeric features, one hot label or ordinal encoding for categorical variables, summarizing data over time across groups, interaction features, creating new variables from combinations like pressure times porosity or crossing with porosity, lag variables, rolling averages, and time since last event. Domain-specific extraction is using physics or engineering formulas to derive meaningful metrics. And then dimensionality reduction is principal component analysis or autoencoders to reduce complexity while retaining signal. Applications for feature engineering in oil and gas is predictive maintenance, production forecasting, and reservoir characterization, among many others. You're extracting vibration trends, temperature deltas, and pressure anomalies from sensor logs, creating time to failure features based on historical downtime patterns, engineer features like rate of change or last maintenance interval. You generate lag production rates, moving averages, and decline curve parameters. You engineer features from metadata. You combine subsurface and subsurface variables for holistic modeling. You can transform well log data into facies indicators using clustering or thresholds. You create composite features and then engineer spatial features from seismic or geospatial data. So we already talked about CO2 injection and CCUS modeling. You can derive sweep efficiency, injection rate gradients, and pressure buildup metrics. Create temporal features to track plume migration over time. Engineer features from simulation outputs for surrogate modeling. Then ESG and emissions analytics, aggregate emissions data by asset, time, and operational phase. Engineer features like emissions per barrel or carbon intensity index. And then use natural language processing to extract structured features from unstructured ESG reports. And then field crew optimization, create features from job logs. Engineer routing efficiency scores and crew utilization metrics, and then combine weather, asset status, and crew availability for dispatch modeling. So here's the best practices for feature engineering in oil and gas. You leverage domain expertise to guide feature selection and transformation. You visualize feature distributions to detect skewness, outliers, and signal strength. Use correlation analysis to reduce redundancy and multicollinearity. You validate features with SMEs to ensure physical and operational relevance. You document feature logic for reproducibility and auditability. And you have to iterate, iterate, and test. Feature engineering is an evolving process. It's not a one-time task. So here are all the model types that I think everyone should take into account, what its purpose is, its technique, and typical use cases in oil and gas. So you got linear regression, logistic regression, decision trees, random forest, support vector machine, k-nearest neighbors, native Bayes or naive Bayes, k-means clustering, principal component analysis, neural networks, and then other neural networks, and then transformer models, gradient boosting, autoencoders, and surrogate models. And I'll give you guys a couple minutes to look at this one. Moving on to the next slide. So, evaluation methods. It's the process of assessing performance, reliability, and generalizability of data science models. It determines how well a model performs on unseen data and whether if it meets business or operational objectives. And oil and gas evaluation is critical due to high stakes, safety concerns, and regulatory scrutiny. You have core evaluation metrics. For regression models, you have mean absolute error, root mean squared error, and R score, an R squared score. So mean absolute error, the average magnitude of errors. Root mean squared error penalizes the large errors more heavily. And R squared score measures how well the model explains the variance. So for classification models, you got accuracy, precision, recall, F1 score, and ROC AUC. Accuracy, percentage of correct predictions. Precision, true positives. Recall, true positives to actual positives. And then F1 score, harmonic mean of precision and recall. ROC to AUC measures models' ability to distinguish between classes. For clustering models, you got the silhouette score, how well clusters are separated. Davies-Bouldin index, how lower values indicate better clustering, and then inertia, sum of square distances within clusters. Then you have validation techniques, the train test split. That's the basic method to test generalization. You have the k-fold cross-validation that reduces variance in evaluation. You got bootstrapping, resampling technique for uncertainty estimation, and you got holdout sets, reserve data for final evaluation after tuning. So applications for model evaluation in oil and gas. You got predictive maintenance, production forecasting, and reservoir simulation surrogates. For predictive maintenance, evaluate anomaly detection using precision and recall. High recall ensures critical failures are not missed. And then you use confusion matrices to assess false alarms versus misdetections. Then you have production forecasting. Use root mean squared error and R squared to assess the time series models. Validate against historical production data and decline curves. Evaluate performance across different well types or formations. Then you have reservoir simulation surrogates. You compare surrogate model outputs to full physics simulation results. Use mean absolute error and root mean squared error for pressure, saturation, and plume predictions. And then you quantify uncertainty and error bounds for decision support. And then you got CO2 injection optimization. You evaluate sweep efficiency production using regression metrics, validate plume migration paths against seismic or sensor data. And then you use scenario-based evaluation to test robustness across injection rates. Natural language processing for technical reports. You evaluate summarization models using Blue, Rouge, or human review. assess clarification or accuracy for ESG tagging or permit categorization, validate hallucination detection workflows using precision and audit logs. So for crew and dispatch logistics, you evaluate routing models using cost savings, time reduction, and service level. Use clustering metrics to validate crew grouping and skill match. And then you monitor drift in model performance and field continuous charge or change. Best practices for model evaluation in oil and gas. You align metrics with business goals. Use domain-specific thresholds, acceptable error for alert rates. Involve SMEs in reviewing model outputs and edge cases. Track performance over time to detect drift or degradation. Document evaluation protocols for reproducibility and compliance. And then integrate feedback loops from field operations to refine models. So here are all the tools that are out there using in oil and gas, their function, their use cases, and some specific notes for them. So there's Petro AI, Averos AI, Altair SmartWorks, Spotfire, OSI Soft, Azure Machine Learning, Palantir, Jupyter Notebooks, Python, Power BI, Tableau, RapidMiner, Google Earth Engine, Hadoop, Spark, and OpenDSS. Give you guys a minute to look at this. But you'll notice that this ranges all the way from info well placement, parent-child dynamics, all the way to harmonizing subsurface and operational data, predictive monitoring, clustering, anomaly detection, satellite imagery for environmental monitoring, processing seismic data, asset performance, ESG reporting, operational planning, sensor data streaming, equipment monitoring, SCADA data analysis, dashboarding, crew logistics, reservoir modeling, production forecasting. And this is not an exhaustive list. This is just a few examples. So, real world project examples. You can use predictive maintenance for rotating equipment. You reduce unplanned downtime to extend asset life. And then data sources are vibration sensors, temperature logs, pressure readings, maintenance records. Techniques used, time series analysis, anomaly detection, feature engineering. The rate of change, last maintenance interval. The outcome was early detection of bearing wear, pump cavitation, and compressor failure. There was a 20 to 30% reduction in maintenance costs and improved uptime across facilities. Tools used were Python, Azure, Spotfire, OSI Soft, Pi System. And you can have the link to the study in this in this link below. But yeah, predictive maintenance for rotating equipment is definitely an application to oil and gas using some of the data sources of what is measured in rotating equipment, and then using time series analysis, anomaly detection, and then feature engineering, you could figure out early detection of um, of some of your rotating equipments. And then predictive maintenance is actually a lot cheaper compared to reactive. So then you have surrogate modeling for CO2 plume migration. You accelerate reservoir simulation for carbon storage optimization. Data sources are full physics simulation outputs, injection logs, and seismic data. Tools use are regression-based surrogate modeling, neural networks, and uncertainty quantification. The outcome is real-time prediction of plume behavior under varying injection scenarios. Your impact is faster scenario planning, reduced computational cost, and improved sweep efficiency. And the tools used were TensorFlow, Altair SmartWorks, Petro AI, and then custom Python workflows. So this was actually a DOE project on carbon surrogate modeling. Then you have NLP powered ESG report summarization and tagging. You automate the extraction of ESG metrics from unstructured documents, annual reports, regulatory filings, and stakeholder disclosures. So IR presentations or data sources. Technique used are natural language processing, named entity recognition, and topic modeling. The outcome is structured ESG database with emissions, water usage, and community impact metrics. And then the impact is streamlined reporting, improved transparency, and faster compliance audits. And then some of the tools use your Hugging Face transformers, Power BI, Palantir Foundry, and custom NLP pipelines. So here are some common pitfalls that come with data science and oil and gas. Everyone complains about the data. So you got poor data quality and integrity. You got incomplete, inconsistent, or outdated records from field logs, sensors, and reports. Manual data entry errors and lack of standardization across assets or regions. Duplicate entries and conflicting formats. And it leads to unreliable models and flawed operational decisions. Then you have data science silos and fragmentation. You have disconnected systems across departments, multiple interpretations of the same data due to lack of unified standards, difficulty in integrating subsurface, surface, and financial data sets, and then hampers holistic analysis and cross-functional collaboration. Then there's a lot of underutilization of available data because there's just so much of it, and the misaligned project goals and KPIs. You have vast volumes of sensors, seismic, and operational data that remain unanalyzed. You have the lack of metadata or documentation that makes data hard to interpret. You have valuable insights missed due to limited data exploration and EDA. And then it creates a gap between data collection and actionable intelligence. Then you have misaligned project goals and KPIs. You've got data science teams may optimize for accuracy while field teams need interpretability. Lack of clarity on business objectives. Models built without stakeholder input often fail to gain traction, and then results in technically sound but operationally irrelevant solutions. Then you have legacy systems and hard to access data. You got critical data trapped in outdated formats, poor documentation and lack of APIs for integration, time consuming data wrangling delays, model development, and then limit scalability and hard time deployment of AI tools. And then finally, lack of governance and ownership, no clear accountability for data stewardship or model validation, inconsistent data standards across assets and regions, ad hoc data cleaning and undocumented transformations. Make sure you document everything whenever you are doing any sort of exploratory data analysis. Documentation is extremely important. And then undermining trust in analytics and compliance reporting. Then when you get to the sexy part of data science, there's also overfitting and model drift and ignoring explainability and ethics. So models trained on narrow data sets may not generalize new wells or fields. Then you have environmental changes, equipment upgrades, or operational shifts cause drift. Without retaining or monitoring, model performance degrades over time, and then it can lead to costly errors in forecasting or maintenance planning. So explainability and ethics, black box models may lack transparency for field engineers. So this is where you have the most resistance to artificial intelligence because a lot of people think it's a black box. And then failure to address bias in training data. The lack of audit trails and interpretability can hinder regulatory acceptance. And then especially critical in ESG reporting, safety systems, and CCUS modeling. Then here are some best practices for data science and oil and gas. You want to align project with business objectives. You want clearly defined goals tied to operational KPIs. You want to engage stakeholders early to ensure relevance and adoption. You want to prioritize use cases with high ROI and measurable outcomes. You want to standardize formats, units, and naming conventions. You want to implement validation workflows for cleaning, profiling, and harmonizing. You want to use metadata for tagging and lineage tracking to ensure auditability, and you want to adopt frameworks for interoperability. You want to leverage domain expertise. It's not about a data science trying to be petroleum engineer. It's a petroleum engineer using data science as part of their tools. You want to collaborate with reservoir engineers, geoscientists, and field operators during feature engineering and model interpretation. Physics inform features and constraints to improve model realism, and then validate outputs against known field behavior and operational benchmarks. And you also want to choose the right modeling approach. You want to match model complexity to data availability and operational needs. Use interpretable models for field deployment. Apply deep learning selectively for unstructured data. And avoid overfitting by using cross-validation and regularization techniques. And then you want to model performance over time, build scalable modular pipelines, and then embed explainability and ethics. Track accuracy, precision, recall, and drift metrics continuously. Retrain models as new data becomes available or field conditions change. Use feedback loops from field teams to refine predictions and assumptions. Then you want to build scalable modular pipelines. Use contained workflows for reproducibility. Automate data ingestion, pre-processing, modeling, and reporting. And you want to design modular components for reuse across assets and use cases. And then you want to embed explainability and ethics. Use SHAP and LIME to interpret model decisions, document assumptions, limitations, and potential biases, and then ensure transparency in ESG analytics, safety critical systems, and CCUS modeling, and then comply with regulatory standards and internal standards as well. And that's everything that I wanted to share with you guys today. I wanted to leave a few minutes for questions, but does anyone have any questions? I see. Would you be willing to share the presentation slides or any supporting documents? Yes, I will be able to. Does anyone have any questions? Hi, Nisarg. I think he might have a question, but I'm waiting.
You are free to unmute also if required, right, ma'am?
Yeah.
Yeah, yeah. Mr. Patel, instead of typing, you can unmute yourself and ask the question if required.
Oh, thank you, Nisarg.
Thank you for this very clear presentation. I'm wondering if you have any recommendation for this low code or no code platform to upscale and to level up quickly our skills in AI and digitalization for oil and gas. So anything that's today we can recommend to
Oh,
catch
absolutely.
up.
Learning Python is very important in my opinion. And then looking at some of the data sets that you already have and then learning how to generate insight from that as quickly as possible is really important. So learning Python, and then if you don't have access to public data sets, Kaggle.com is a good place to get free data sets. It may not be related to oil and gas, but it's good to get free data sets there.
Great.
Which path to take in line with data science, which will be in line with petroleum? So you can use data science for any kind of petroleum engineering subdiscipline. Reservoir engineering is kind of the closest to data science, like to the immediate application of data science. But I would also argue like you have drilling engineering too by looking at different drilling metrics as well. So reservoir and drilling, I would suggest that you can easily apply data science to. And this is assuming that you're taking a petroleum engineering route. Of course. Does anyone have any other questions?
Good day. I might not get the pronunciation right, but Yogashri. My name is John Paul from Nigeria. I'm a 500 level petroleum and gas engineering student, and I'm heading into my final year practically in a couple of months. So I've been trying to think about like a very good niche in petroleum engineering to work on for my final year project, and I want to very much apply data science. And I've not really been able to come across anything. I'm just trying not to do generic because you look at drilling engineering, they probably have directional drilling. But I'm just thinking, are there any suggestion of the top of your tip? I want it to be something that is actually like a problem that is solvable, and I can actually just do one or two research, apply data science, and come up with something really good for my project. So, any suggestions you have for me? Thank you.
My suggestion is go to Journal of Petroleum Technology, JPT, SPE's JPT article. Look at the latest things that are being talked about in JPT. Come up with a question and try to get some data out of that question. And then the SPE data repository is also, if you're an SP member, you can have access to the SP data repository for that data. So that's where you can get
Okay,
data
thank
set.
you. Thank you. I've not heard of the data repository before. So thank you for that. I would look at those and recommendations. Thank you.
Of course. Does anyone have any other questions? Well, if not, thank you so much, everybody, for listening in and to tuning in.
Um, yeah, thank you, ma'am, for the wonderful session, and thank you for the people who have joined around the globe for the same. And I think we can wind up with that. So I'm closing the session with your permission, ma'am.
Sounds good.
Sure. Thank you. Bye.
Bye.